Welcome to our third workshop of STEM for All. We'll be going over number theory. And before we start this, I just want to introduce the team, including myself, who goes beyond planning these workshops, preparing logistics and slide decks for it. So I'm Varun.
Hey, I'm Yajat.
Hi, I'm Ridhu.
I'm Zoya.
And we have another member who's not present as of right now. So hopefully we can see them in the next workshop. So the table of contents for this meeting is we'll be going over modular arithmetic, and then we'll be going over prime factors and prime and factors, including like prime factorization, and we'll be looking at some contest questions for those. And finally, the Diophantine equations. Yajat will go over that near the end.
Okay, first starting off with modular arithmetic. So the main formula for this is A is congruent to B mod n. And so this means when A is divided by n, it'll give A the remainder of B. So for example, think about it like this. So 13 would be equal to 3 mod 10. So you should probably see the pattern by here. So another thing that goes along with this is digit cycles. So if you see in the top right, I think about it like a clock. So it basically like repeats. So here, like if you take 9 and you add 4 hours to it, it would just go back here. So that's similar to the pattern that we see here. So for another example, if it was 10, this would just be 0 mod 10 because it's no remainder. Like that. So like I was saying, digit cycles. So this means to calculate large digits of a number, a to the power b, look for a pattern by computing the first few values and then seeing that the pattern will repeat for larger values of b. So some of y'all might have seen this at school with imaginary numbers, and it's similar to that. So here are a few problems. You won't really need digit cycles for these if you can figure out how to do it with the pattern I showed before. So I wanted to give you all a few minutes to just try it on your own, and then we'll go over them. Okay. I'll start explaining the first one, and then from there you can try seeing if you can do the second two. So the first step of this would be to divide the base, so 36 by 5. So if we do that, 36 divided by 5, we would get 7 with the remainder of 1. So if we write this with mod, that would just be 36. Oops. 36 is congruent to 1 mod 5. Like that. And so from here, we can then apply the exponent to the numbers. So that would just be a 9 here and a 9 here. And so to find the remainder, which would just be 1 to the power of 9, and that clearly is just 1. So that's how you find the remainder for large exponents like that. And so another way to solve it would just be using digit cycles and seeing when it repeats. So you can try doing that with 34 here as well. And the only difference here is that it won't be the same when you divide it by 5. So 34 using mod would actually just be -1 mod 5. So this might be a little confusing since you can't really get -1 as a remainder. But the thing is, if you think about it this way, so 34 would be 1 less than 35, which is a multiple of 5. So you can also write it as just -1. And so here, when you apply the exponent of 9 on both sides, -1 to the power of 9, because it's odd, would get you -1. So that's the answer. Oh, that's the answer for this one. So you guys should start to see like how you can use mod, and then from there start figuring out the answer. Okay, next question. Okay, so this says an integer n is selected at random in the range 1 is less than or equal to n is less than or equal to 2020. So what is the probability that the remainder when n to the power 16 is divided by 5 is 1? So that's basically asking when n6 to the power 16 is divided by 5, how likely is it that the remainder will be 1? So first, we can start off by thinking about what it's like trying to say. So it's basically showing how n, when divided by anywhere from 1 to 5, so this is because 2020 divided by 5 would go evenly. So any of the cases would be like n is congruent to 0 mod 5, n is congruent to 1 mod 5, and so on like that. So I'll write that down here. So when you put the exponent to this, so to 16, 16, you would just get 0. So 0 to the power of 16, which would just be 0 mod 5, basically. So this means the remainder would be 0. So if we think about it, the next case, n, and do it with a remainder of 1. This would be n to the power of 16, and then 1 to the power of 16, which would, in this case, just be 1 mod 5. So you can see here how the remainder is 1. And so we want to keep finding these cases where 1 is the remainder. So we'll take n is congruent to 2 mod 5. And so if we take n to the power 16 for this one, we could write it as n to the power of 2 to the power of 8. And then similarly for the 2, we could do that as 2 to the power of 2, and then power of 8. And then simplify that. 4 to the power of 8. And then think back on negative rules. So if we do mod 5 for that, this would just be -1. because 4 is 1 less than 5. So negative 1 to the power of 8, and this would once again just be equal to 1 mod 5. So the same as up here. And so once you continue doing that, so try doing that with n is congruent to 3 mod 5, and you'll see how the pattern continues, and you would just get 1 mod 5 again. And then for n is congruent to 4 mod 5, then n to the power 16 and 4 to the power 16, so like I just showed you here, would once again just be negative 1 to the power 16, which would once again 1 mod 5. So as you can see, for these different cases, so think about one where n is congruent to 3 mod 5, only n is congruent to 0 mod 5 is the remainder not 1. So this means 4 out of our 5 cases, the result was 1 mod 5. And so, like I said at the beginning, since each case occurs equally as 2020, mod 5, or like 2020 would be congruent to 0 mod 5, because 5 divides evenly in that. So then our result would be 4 out of 5 as the probability, because only 1 doesn't work. So that would be our final answer, 4 out of 5. Okay. Next problem. Okay. For this problem, it says find the remainder when 9 times 99 times 999 times a lot more higher digits. So 999 nines. So that's a lot. And then it says find the remainder when it's divided by 1,000. So this, obviously you can't multiply this by hand. So here is when we start using mods and the negative versions of them, like we did in the second problem. So we can first start off by seeing it digit by, or number by number. So start with doing 9. So 9 would be congruent to just 9 mod 1,000, because the remainder when divided by 1,000 would just be 9. Like that. And then you would continue in for 99. And so this would just be 99 mod 1,000. Okay. So like that. But for the next one, you might think it would just be 999 because it doesn't divide evenly. But one way we can write it is as -1. So -1 mod 1,000. Because like I said before, like 1,000 minus 1 would 1,000 minus 1 would get you 999. So it'd be 1 less. And so if you see that for like a bigger number, so I don't want to write it all out, but if we had like quite a few 9s, it would just repeat that. So it would still just be -1 mod 1,000. And this is because any multiple of 1,000 from now on, -1 would get you the number on the left side of it. So if you see this pattern, it's 999, and then all of the ones between that are just -1. So we can simplify this equation to be just 9 times 99, so I'm multiplying the remainders right now over here, times -1, and then ... continue that -1, or, because we know how many they're going to be, because it says here, so times that, -1 to the power of 997. So see if you can understand why it's 997. So this would be because of how many there are here, 999. And then we already have the 9 and 99, so we can subtract that, and we would be left with 997. Because 999 minus 2 would just be 997. So here, because 997 is odd, this whole thing would just be equal to -1. So cross that off, and it's just -1. And then if you multiply that out, you get -891 mod 1,000. Which would then, to make it a positive number, we could just write that as 109 mod 1,000. Sorry for my bad handwriting. So 109, which would be our final answer. So basically, to sum up, we found the pattern of this. So kind of like digit cycles, where we did 9, and then got the remainder of 9 for mod 1,000. Same with 99, and then found that the resulting patterns would just result in -1. And so we multiply that by the number of terms there would be, so 997 negative ones, and just resulted that in -1. And then you multiply that out and just make it positive. Okay. Okay, this would be our last problem in mod. So this one's a bit complicated. So here we start off by, okay, so one of the following numbers is not divisible by any prime number less than 10. Which is it? So we can start off by finding the prime numbers less than 10. So this would just be 2, 3, 5, and 7. So here's when we start using digit cycles. So I can write this out. So let's start off with 2 on here. So 2 to the power of 0, 2 to the power of 1, power of 2, and 2 to the power of 3. Like this. And so try to find the remainders with mod 3. Or yeah, so for mod 2, one thing we can figure out is just see here, look at the numbers. So 606, because that's an even number, you would easily divide by 2. But when you subtract 1 from it, it would no longer be like fully divisible with no remainder. Same for the rest of them. You're adding 1, and it would continue like that. So we can just cross out 2 and then move on to 3. So that's why I'm looking at mod 3 right now. So 1 mod 3. And so this is where you would continue doing that for the rest of the prime numbers as well. So try to find the pattern with them. And if you see here, it starts repeating. So 4 mod 3 would just give you the remainder of 1 again. So here it would be 2 mod 3. So if you see, the even exponents would equal 1, and then the odd exponents would have a remainder of 2. So we can start by checking with each of the answer choices here. So 2 to the power of 606. So 606 divided by 4 would get you a remainder of 2. So 2 here would be like the exponent that we're looking at, because we can just move 2 to the power of whatever, and then 2 to the power of 2. So that would be this right here. And then if we subtract 1 from that, that would actually just be 0 mod 3. So 1 mod 3 is what it's equivalent to, mod 3. minus 1. So that's what it's equal to. And we would just set that to 0 mod 3. Or just, as we can write it here, 0. So that means A is divisible by a prime number. The prime number in this case being 3. So we can cross A off as our answer choice. And so you could try that with B as well. And so in this case, it would be 1 mod 3, right? But when you add 1 to it instead, it would be 2 mod 3 instead of 0. So this isn't divisible by 3. So we'll try C. In this case, it would be 2 mod 3 over here, because it would be 2 to the power 3. And then if you subtract 1, that would just be 1 mod 3. So still does not work. Then for D, if we look at it here, it would be 2 mod 3 as well. Which we just figured out in C. But here, because we're adding 1, this would just result in 3 mod 3. And 3 mod 3 would just be 0 again. So once again, this is 0, and it's divisible. That means D would also not work. And then for E, when you look at it, this would be odd, so 2 mod 3, and then 3 would divide easily. So you would just get 2 mod 3 as your final. So this would also not work. So like I said, so let me just repeat that again. So 2, 6, 7 would be over here, same as this. But then 3 to any power would be evenly divisible by 3. So then it would just be 0 mod 3. And so that would just result in just this. So once again, it would not be divisible by 3. So then you do the same. So try this on your own. I'll give you a few minutes to try 3 and 5. And then once you, or we already did 3, right? So cross that off. Try 5 and 7. And then if you notice, so once you go, you should only need 5 to get your final answer, because 5 should cross off 2 more. So I'll give you a few minutes to do that. Okay, so far you should have been able to find the digit cycle for 5. So it'd be 2 to the power 0 equals 1 mod 5, 2 to the power 1 equals 2 mod 5, 2 to the power 2 would be 4 mod 5, and then 2 to the power 3 would be 3 mod 5. And then here the cycle repeats, so it has 4 different possible remainders. And so from there, you could try that with B, C, and E, the leftovers, and you should be able to cross off B and E, since 206 would give you a remainder of 2 when divided by 4. So that would just be 2 to the power 2 equals 4 mod 5 plus 1, which would be 5 mod 5, or 0. So you can cross this one off. And then E, you can try it as well. One thing about here is 3 to 607 could also be written as negative 2 to the power of 607. Because if you think about it like mod 5, then 5 minus 2 would get you 3. So that's how you can write it as this. And so this is the hack that you can use a lot. with negative numbers. And so here, if you just see like this is the opposite of this, you can just subtract it, and that would once again just be 0. So you can cross this one off as well, and your answer would be C. Okay. Or let me leave that up for a sec. Okay. So A and D were divisible by 3, and then B and E were divisible by 5. So we don't even have to check 7, and we can be sure of C. Okay, moving on. Primes and factors.
Okay, so now I'll be talking about primes and factors. So just a quick introduction. Prime numbers are numbers that have exactly two factors, one and the number itself. So just in case you're not familiar, a factors is a term that divides into another number evenly without leaving any remainder. So it should be divisible just like that. There should be anything left over. And the opposite of a prime number is a composite number. So if the definition for that would just be the exact opposite of a prime number, there would be factors beyond one in itself. So 2, 3, 5, 7, 11, 13, 17, 19, 23. All of these numbers, what they have in common is other than one and themselves, they have no other factors. So now we're going to be talking about prime factorization, which is something that's really critical in number theory contest problems because contests try to see how you know how to build up, how to compose a number. And prime factorization is a tool that would help you deconstruct a number. So prime factorization is a way to express a number as a product of primes. Every number can be written uniquely using prime factorization. And why this is so important is because for questions where you want to break down a number, or they might ask you, like, do you have a product of this? And then what can those products be added up to? If you want it, you can't really eyeball those type of questions. You would need to use prime factorization to solve them. So for example, if you wanted to break down the number 360, if you actually use prime factorization, it's nothing but 2 to the power of 3 times 3 to the power of 2 times 5. And how we get into this conclusion is what I am going to be, which I'm going to explain. But as you can see, the number should be deconstructed through bases of primes. So moving on to the next example. So I'll be going over the prime factorization of a number, 120. And in order to do this, I want to start off by saying, let's write down the top number here, okay? Now, just from the chart below, I'm going to list down some numbers of primes because that's going to help us deconstruct it. And one key thing is most of the times when you do prime factorization, you're only going to get numbers that are with like the first few short answers. You're not going to get like a big prime factorization number like, I don't know, 19 or something beyond that. Like, I can't think of a big one in my head, but you won't get something that large. You'll mostly get between 2, 3, 5, 7, rarely 11. And one second. Okay. So what I'm going to do is I'm going to write down the early prime numbers. This can be able to help. So 2, 3, 5, 7, and 11. And it can go on. What I want to do is I want to see what numbers I could break down 120 into. So to start off, the easiest one is if you see it's even or odd. If it's even, it's going to be 2. 2 would always work out. So 120 can break down into 2. And because you've done 2, now you have to do 120 divided by 2, which is 60. And now you broke it down to officially your first set. You have 2 times 60 makes 120. But obviously we can keep going. And 60 is another odd number. Sorry, even number. So we could do another division by 2, which is a prime number, and that becomes 30. And 30 is another even number. So we can keep on using prime numbers to deconstruct this number. Let's get 2 and 15. Now, we were done with even numbers, but 15 is still composed of some prime numbers. One that comes to mind is 5. So we can use 5 and 3. And the moment you stop at a prime number is when you finish the prime factorization. So the final number I have here is 3. 3 is a prime number, and a thing we know about a prime number is it cannot, other than 1 and itself, it has no other factors. So we're officially done with this number. And now that we're done with that, we go back to the start, and the numbers you have on the left side, you wanna note them down. So 2, 2, 2, and 5. So that means these are all the products we have. So that means 2 times 2 times 2 times 5 times 3 would equal to 120. And using exponents, we can just say that 2 to the power of 3 times 3 times 5 equals to 120. And why this is so crucial is because using this, we know all the factors of 120. So for example, if you quickly asked us if 15 was a factor of 120, we could see that we have 3 and 5 as a factor. So we know that 15 can divide into 120 perfectly. Or if you wanted to ask if 12 was a factor, we can see that you have 2 to the power of 2, which makes 4, and you have a 3, which is 12, and it will divide in perfectly. So we're gonna see a few more contest questions that actually use prime factorization. So problem 1, Kiana has 2 older twin brothers. So twin brothers, so something that should come to your mind is twin brothers means that they will be the same age. The product of their 3 ages is 128. What is the sum of their 3 ages? So starting off the bat, if you see this question, you see that you have twin brothers. So if X is going to be the twin brothers, then we'll let Y be Kiana. Sorry, I spelled brothers wrong. Yeah, just brothers. Y would be Kiana. So in that case, don't get fooled by the question and try looking for 3 variables or anything like that. That's one of the contest tricks that are there. And x times y equals to 128. And they're asking for what x plus y would equal to. So 2x plus y. So I'll give you guys a few minutes to solve this question, and obviously the hint here is you would need to use prime factorization. So and if you guys have an answer, just feel free to message me in chat. I can let you know if it's right or not. Okay, so I got a few answers in chat, so most of them look correct. So I'm going to begin this question. So let me just clear this. So to start off with this question, when you see product of 3 ages, you want to decompose this number 128 because you have x times y equals 128. I want to deconstruct this 128 to see what I can get. But for those who did the prime factorization of 128, something you would find out is, so let's just do it. So 128, based off our prime numbers, 2, 3, 5, 7, 11, to 128 to even number. So you can go 2 and 64. And 64 is another even number, so you can go 2 and 36. Yeah, and 36 is another even number, so you can go 2 and 18. And 18 is another even number, so you can go 2 and 9. And 9 is an odd number, but it has a factor of 3. Let me just see if, oh, I think I made a mistake. Yeah, it's not 36. Oh, oops. Let me just quickly delete this. It's 30, my bad about that. It's 32. And then if you break 32 down again, that becomes 2 and 16. Yeah. And if you break this down, that becomes 2 and 8, 2 and 4, and then 2 and 2. So 128 is just 2 to the power of 1, 2, 3, 4, 5, 6, 7. So 128 is just 2 to the power of 7. So considering that, we need to find a number of, so two similar numbers and one number that goes up to 127. So I see times x times x times y equals to 2 to the power of 7. One thing I know is all of these numbers have to be to the base of 2. So 2 times 2 times 2 equals to 2 to the 7. And considering I need to add up to 7 and I have 3 numbers, I know that these two numbers have to be the same. So a set of numbers that in this case that would work would be 3, 3, and 1. So that means that now that we have these two numbers set, we know we have 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 1. And using our exponent property, we know that 3 plus 3 plus 1, this would work out. And based off that, we know that now that this product works, all we have to do are add these numbers. So if 2 to the power of 3 equals to 8, you would get 8 plus 8 plus 2, which equals to 18. So the sum of the three ages would be 18. Okay, so moving on to problem number 2.
Okay, so the 25 integers from -10 to 14 inclusive can be arranged to form a 5 by 5 square, in which the sum of the numbers in each row, each column, and the numbers along each of the main diagonals are all the same. So what is the value of this common sum? So I'll give you about like 2 minutes to try this out. Okay, so in this square, like all the rows, columns, and diagonals have the same sum. So since there are 5 rows in the square, each row must have the same sum of numbers, meaning that the sum of all the numbers in the square divided by 5 is the total value per row. So to solve this, we would add up all of the integers from -10 to 14 and find the sum of the 25 integers. So from this we get 50, and then we can divide this by 5 to get the total value per row. So we end up with 10.
All right, so now the last portion of our workshop today is going to be Diophantine equations. So, um, Diophantine equations is probably something new that's to everyone. So in standard algebra, we usually look for any numbers that fit into decimals, fraction, or even irrational numbers like pi. But Diophantine equations only look for numbers that are integers. So we're looking for whole solutions, and it's kind of like thinking about like counting people or coins. You can't have 2.5 people inside of a room. You can only have 2 people or 3 people. So again, that's what Diophantine equations are looking for. So our biggest strategy here is to take moduluses of the numbers, right? So we want to take those mods and we want to take we want to see which equations we won't be able to get and which solutions we will be able to get. So if the remainder is on both sides of an equal sign don't match up, we immediately know that no integer solutions exist. So let's get into more details about Diophantine equations. So one thing to keep in mind is bounding. So this is when we figure out the maximum or minimum possible values a number could be. So if we can prove x has to be between 1 and 10, we've already turned an infinite search down into almost a 10-second search where you're only checking for numbers between 1 and 10. Second thing about Diophantine equations is factoring. So we can break a complicated expression down into more smaller pieces to find all the possible solutions, and we can do that by factoring. And then substitution is the last thing, where sometimes an equation can look really messy with a lot of variables. So to simplify it, we can substitute things in. So for example, if we know number a is a multiple of 6, we can just write it down as a equals 6k, and that makes the math a lot easier to look at and calculate. So let's get into problem number 1. So which of the following expressions is never a prime number when p is a prime number? So I'm going to give you guys a couple minutes here, and we will get back in around 3 to 4 minutes. All right, so I hope that was enough time to at least get a start on that problem. So again here, which of the following expressions is never a prime number when p is a prime number? So here we know that we're looking for which one of these expressions is never a prime number when p itself is a prime. So the trick here is to first realize that we want to use modulus 3 as our filter, right? Because that's something that's divisible throughout all three or all five of these answer choices. So what we want to do is that we first take a small prime number like p equals 3 in this case. So in that case, we can first dive into this by looking at options C and just option C. So we can see that option C is p squared plus 26. And we know that if we take 3, we sub in 3 for that. 3 squared becomes 9 plus 26, and that ends up being 35, which is not a prime, right? So now let's look at all of the other prime numbers. So almost all primes, we got to think about this logically. So almost all primes except for 3 have a special property. When you square them, the remainder is always 1 when divided by 3. So this is kind of our biggest superpower here, realizing that trick. And that allows us to cross out and realize what the other answer choices are and how to get to that problem. So if p squared always leaves a remainder of 1, then p squared plus 26 becomes 1 plus 26, which is 27. So this is immediately how you get to this answer choice. And we realize that when p squared, I can write it out here. So p squared plus 26, when keeping in mind that when you square any prime number, the remainder is always 1, and when you divide it by 3. So when this would become 1 plus 26 equals to 27. And so since 27 is a multiple of 3, the entire expression p squared plus 26 will always be a multiple of 3 because a multiple of 3, which is greater than 3, can never be prime, right? Using the logic we realized earlier. So we found our answer choice number C. All right, so now next, let me clear that. And let's go to the next problem. And this is going to be our last problem for today's workshop. So problem number 2. How many 4-digit integers A, B, C, D with A not equaling 0 have the property that the three 2-digit integers A, B is less than BE, which is less than, or sorry, that should be BC, that's a typo. So AB, which is less than BC, which is less than CD, form an increasing arithmetic sequence. So one such number could be 46 or 4,692, where A is 4, B is 6, C is 9, and D is 2. So I'm gonna give you guys around 2-ish minutes here, so you guys can dive into that. All right, let's dive into the solution for problem number 2. So going over it one more time. So how many four-digit integers within A, B, C, D with A not equaling 0 have the property that the three two-digit integers A, B is less than B, C, which is less than C, D, form an increasing arithmetic sequence. One such number is equal to 4,692. So first thing we're going to do here is that we're going to use 4,692 to build around and solve for the method, right? So we're using this as our guide because that number is already given to us, so we know how to think of our own number. So first thing we're going to do is name the three two-digit numbers. So first we're going to have AB equals 10A plus B. Next, we're going to have BC. Oops. Let me go back. Okay, we're going to stick with BC equal to 10B plus C. Let's add that back. Last, we have CD. Oops. Can we go back? There we go. CD is equal to 10 C plus D. All right. So next we need to write out our conditions. So for any arithmetic sequence, we have to realize that the middle term doubled equals the sum of the outer two. So to put that into numbers, we can do 2 times BC is equal to AB plus CD. And then we can expand that out by saying 2 times, so we can take BC from here. We have 10B plus C, and then we can substitute the rest in right here. 10 plus B, sorry for my handwriting, plus 10C plus D. All right, so now that we have that listed out, we can expand everything out and you're going to end up with 20B plus 2C equals 10A plus B plus 10C plus D. All right, so once you get to this spot, we can solve for D. And that is the kind of the key equation that we're looking for. So D is going to be equal to 19B minus 8C minus 10A. All right, and now that we have this, we can plug in our numbers from here, right? And we're taking our example number they gave us, and we're gonna end up with everything simplifying down to equaling 2. And that works, right? And we notice what this means. Once you pick B and C, the value of 10A plus D, right? 10A plus D is completely fixed, meaning A and D are determined for you. And you're really just counting valid pairs of B and C. So next, we had to figure out when the pair BC is valid. So two conditions must hold for this. The first condition is that 19B minus 8C must land in between 10 and 99 so that a real digit 1 through 9 and D is a real digit 0 through 9. The second condition is that the sequence must be strictly increasing, meaning that C has to be greater than B and okay, so this is that was the next step. So those two conditions are what we're using to figure out when BC is a valid pair. So next is a little bit longer. So you guys can take a second to look at this. I'm gonna clear the screen now, and we're gonna move on to the last portion, which is counting the valid pairs of BC within C is greater than B, right? So I'm not gonna write it all out, but I will say it verbally. So when B is equal to 1, there's no valid values of C. So our count is gonna be 0. When B is equal to 2, there are 3 valid pairs of C, making our count 1. When B is equal to 3, valid values of C are 4 and 5, uh, making our count 2. There we go. And then when B is 4, we have 4 valid values of C, which is 5, 6, 7, 8. So we're going to add 4. Next, for when B equals 5, we have 4 values again of C that are valid, 6, 7, 8, and 9. So we're going to add another 4. And then for 6, we have 3 values of C that are valid, 7, 8, and 9. So we're going to add a 3. For B equaling 7, we have 2 valid values of C, 8 and 9. So we're going to add 2. And then for 8, we have 1 valid value of C, which is 9. So we're going to add 1. And then for B equaling 9, there are no valid values of C, so our count is 0. So we're going to add a 0. And then when you combine all those together, you get 17 as your final value. So we can verify that 4,000, so that our example number 4,692 has B equaling 6 and C equaling 9, and that's right there in B equals 6, right? So our table, the one that we would have drawn out, includes that correctly. So that is how we get to figuring out this problem. So 17, if for any of those like who got to solve it all the way throughout, if you guys got 17, congrats, that was a really tough problem. And next we're gonna be skipping the challenge problems for today, and I'm gonna let Varun take it over for.
Okay, yeah. So first of all, I'd like to thank all the presenters, Yajat, Ridhu, Zoya, for presenting and getting with the slide deck. I thank you all for coming to this month's workshop. You guys can check your email for the next month's workshop. If you guys have any questions on any of the topics, feel free to stay and ask us. But on that note, have a good long weekend and we'll see you next month.